Hello everyone. Today I'll start one of my JavaScript based series that will be on decomposed math functions such as exponential, ln, log, square roots, cube roots, anything like that. Uh, in this video I'll talk about the nth root, um, so how to calculate it. And you obviously be able to calculate both the square root and the cube root throughout this function. So in some sense it seems hard to compute or like pretty much exhaustive, but when you think of it, it's really easy. And if you want to see a particular malfunction, like or maybe binomial, the binomial CDF. Just ask in the comment and I'll see, depending on how many requests I have toward this function, I'll um, see how I can do it, then I'll post a video about it. So let's start. So already created a file, HTML file. So as you can see, there's only this. Um, I could have put the HTML body head stuff, but it's not necessary in this case. So let's start. So let's let's read the function. So we'll call it nthroot. So I'm pretty sure that this method doesn't exist at all in this name. When you use it with the math object, your x, and obviously your n. So here, we'll create a simple function that inputs the x term and the n, which will be the nth. So this, if it will be 2, it will be a square root, it will be 3 a cube root, and 4 and out in fourth root, 5th root, and etc. So, before starting, uh, cube nthroot is basically the inverse of the polar n. So n to the nth root is the opposite of the result of this calculation to the power of n. So, I would an efficient way to do it is just trying to get an a guess number of the results of the operation and fixing it in a way that to get precise enough to be equal to the x term when it will be to the power n. So let's start. So so my guess variable will be the a, or simply I'll just leave it as an a, and so I'll start with this as we want to take into account these wide array of possible x, such as that you can have 2 or 4 as your x, here 2 as your n, so this will be straight the answer. And so I'll do like complicated stuff to confuse you, like trying to find the closest root of x x. Um, but as you may know, it's intended to get closer to the um, correct result faster and leave less job to the main core to the core part of the assumption. So just make a quick verification. So if a times um, so now we will check if n to the power n equal x. So if it's higher, I'll just decrease it by one. So now we'll go to the main part, which is obviously the most interesting part. And 20. So this 20 here is, so you can leave it as 20 or 10 or 60. I will leave it at 60. Um, depends if you want to be more precise or more like be sure that you will get um, your computer correct the most accurate result, even though um, you could get infinite number of digits, but it still get um, pretty much closer than if the loop starts only runs 20 times or even 10 times. So, let's see. So A will be 1, 2. So we'll increment it to x minus a squared multisecond. So oops, a to the power n as it take as it's valid for every root divided by um, let me see. So for all of you who don't know that um, this is not um, is not equal to the a to the power n in some browsers, including Google Chrome. Also, suggest you to use this as you will be sure, because I'm not sure why, but it's not the same meaning now. So here will be a plus 1, so the next term to the simple minus itself, so that means a to the power n. So what I'll do is basically trying to adjust depending on the distance between x and the a power n with preciseness of this, which is simple characters like this. It will adjust whether by adding or taking off a to be more precise. So whether if you don't do this, and you give, for example, the a, the first term is too high to be the actual root and root of x, this function we will fix that. Maybe we might be less accurate than if we have something like this that will uh, simplify the job. We'll still get the pretty much the same answer with a big number of rows. For example, 60. So that's it. So return A, obviously. And now let's try it. So I'm going to open and separate. And I'll just execute it. Correct. X. And so, and next, let's say 127. Oh, oh yeah, stupid mistake. 127 days. So to the so I want to describe it. Ah, oh, just for this things. All right. And plus it. Okay. And just some space. And that basically should work. There you go. So I'll just check on the calculator to see if it's correct. And so I'm not into every digits. Just to make sure it's more or less correct. 269, 287, 689, yeah, yeah. So it doesn't always include that it's like it's precise, but you get the idea. Just to show you something, we're going to put it at 6, so 10 times less, and then just minus it, and then you see it changed, and it's not so correct, so it's 3, 2, 7, 8, 80. So as you can see, the 669 font isn't there, and so I'll just run it. So another number with some 245, 404, random. So just check it. 255, oops, 4, I'll just get there to excuse me. There you go. There, 6, 8, 4, 8, 6, 7, yeah. So I'm pretty sure that the system can only display that amount of decimals, but I'll try to fix that. Oops. Let's say 50, maybe too big. And sorry for the inconvenience update. Yeah, so that's just the separate that's just WebKit limits of display numbers and digits. So I think on Chrome, even though it also uses WebKit, you can display more. You might make mistake in other program. So that's basically it. If you want to code uh, like it is, auto always use um, perfect nthroot estimation, also the or they simplified like this those two lines. If you want this part, I click on the final remote one and just tell me in the comment on PMU the whole code. So I hope you enjoyed. Thanks for watching. Don't forget if you want to see a particular function, don't forget to comment it, and I'll try to place it in a part of the series. And the next one will be the exponential, so Napier's, uh, so the Taylor series. So, so if you have any ideas, uh, don't hesitate to comment them.